Good. So, any what did we do last time? Okay, I mean, yeah, we just went through without any proof. Actually, last time I didn't give any proofs of the statements. It was just basically, I mean, just telling you of some facts. Huh? The reason, I mean, there is no point in going through those proofs because really you will never need it. You see, more important is to just know that there are these statements, there are these facts. Huh? So one thing was that Riemann integral was not. I mean, the whole problem was that when you look at the, I mean, you cannot just restrict yourself to the space of continuous functions because that's not a complete space. Huh? Because if you take a sequence of continuous functions, it may end up with the discontinuous functions. Huh? So you have to enlarge the space, and therefore you have to also modify the definition of integral, right? The Riemann integral was defined for continuous functions, but now since your space includes discontinuous functions, you need to modify that. By the way, I mean, Riemann integrals can still work if there are some, finite number of discontinuities, because you can always do the integral piecewise. For example, if there was a function which was discontinuous, so I don't know, let's say there is some x here, and the function is something like this, and here it jumps up at some point, then you can, and you want to integrate it, you can always integrate from, say, this point to that point, and then another integral from here to there, right? So each of these integrals is well defined because in this range it's continuous, and in this range this is continuous. However, the problem with the Dirichlet function that we gave, the example, where remember Dirichlet function was equal to 1 when x was a rational number and was equal to 0 when x was irrational. There you cannot do. I mean, there is simply, the Riemann integral simply doesn't work. Okay. So for this reason we had to extend the definition, and okay, I didn't define to you properly how the Lebesgue integral is defined, but okay, there is a definition and that can handle such discontinuities. Okay. The important point about Lebesgue integral that one should remember is that the measure, Lebesgue measure for a countable set of points is 0. Okay. So that is that's the only thing which you need to remember really from the Lebesgue. And then what else we did last time? Then again I stated this Reece-Fischer theorem, which says that the L2 spaces. I mean, we defined the L2 spaces, right, which are the space of square integrable functions with some weight w in the Lebesgue sense. So this was called L2W, L2W AB. Okay. So this space was the space of all functions which were square integrable, okay, in the Lebesgue sense with weight function w in the interval a to b. And the Reece-Fischer theorem says that this space is complete. Okay. So this is the important point. So these L2 spaces are really what are the spaces which are used in quantum mechanics, right? Those will be the Hilbert space of states and so on. But of course, in quantum mechanics, you never worry about these discontinuous functions, right? Because there is another very important statement, which again I will state now without any proof. The statement is that if f belongs to, let's say, if f of x belongs to this L2W spaces, then you can always write f as a limit of a sequence of continuous functions. Okay. So then there exists a sequence of continuous functions, and that's the important point. Continuous functions. Okay, this is the important point here. So I will just call f1x, f2x, fnx. Okay, this infinite sequence which converges to this f. Okay. When we say converge, again, it's in the sense of almost everywhere. Okay, you remember there was a distinction between I mean, so it converges almost everywhere. Okay. This is an important statement again. That there is so any function f, this may not be continuous function, but the only thing is that it has to be in the L2 space, which means it should be square integrable in the Lebesgue sense. Then the statement is that such a function can always be represented as a limit of a sequence of continuous functions. Okay, and it's because of this that you never, in practice, you never really have to worry about more complicated functions. You can just work with the continuous functions. That's why, I mean, in all this quantum mechanics course, you were always working with continuous functions, right? The reason is that even discontinuous functions, but which are part of L2, can be represented in terms of as a limit of a sequence of continuous functions. So you can do everything with the continuous functions. You don't need to, do anything with these complicated functions there. And for the continuous functions, you can just use the Riemann integrals. There's no problem, because Lebesgue integral is the same as Riemann integral for continuous functions. Okay. Now, so what other things we said? Yeah. Complete means that, so yeah, in this, I think it's closed or complete is the same. Maybe last time I was using the word closed, is the same. So the statement is that if so this space is called complete, or if you take any sequence of vectors in that space, right, which has a limit. I mean, so let me repeat that just because again it's important to complete. I think last time I was using the word closed, but in the book it is the complete is what is used. So I will now use complete, this term complete. So a space is called complete if for any sequence, let's say f1, f2, fn, which is inside which is in this space, such that which satisfies the Cauchy criteria, which satisfies Cauchy criteria, which is what? What does it mean? It means that fk minus f, I mean the rho, the distance between fk and fl goes to 0 for as k and l go to infinity. So the distance between, okay, if you wish, I can use a bracket notation. Okay. So the distance between the fk and fl goes to 0 in the limit. This is the Cauchy criteria, right, for the convergence of a sequence. Then so they should converge according to Cauchy criteria, but it may happen that it converges to something which is not in the original space, right? As we saw in example, that if you just take the space of continuous functions, you can find a sequence of continuous functions which satisfies the Cauchy criteria, but the limit function is not a continuous function, right? So that will be an example when the space is not complete. Okay. So a space is complete if the limit, I mean if the sequence which converges to some limit still belongs to the original space. If that happens, then you say that that space is complete. Okay. So now today we will go ahead and start constructing. Oh, incidentally, yeah, I think towards the end I mentioned about this orthonormal basis, right? And yeah, the definition of orthonormal basis was, I cannot find it. Where is it? Yeah, we defined the orthonormal basis as orthonormal basis E1, E2, etc. Okay, there's a set here, and this will be a basis. So of course, orthonormal means, of course, these are all orthonormal to each other, right? But it's a basis if the only I mean, so this is a basis if any vector which satisfies any vector A, let's say, which satisfies the condition EI A equal to 0 for all of this, for all I, okay, then such a vector must be, then A must be trivial, A must be null vector. Okay, this was the statement. And then we said that if you take some f and you can compute this coefficients fi, which is simply EIF, okay, for each EI, for all I, okay, and then you can construct a sequence of vectors fk, which is equal to fi EI, I going from 1 up to k. Okay, we construct the sequence of vectors. Then we showed that this fk converges. I mean, we actually, I don't know whether I proved it, or anyway, it was the basic statement was that fk converges, k goes to infinity, to f itself. Okay. Again, this convergence is in the sense of, you see, when I will say converge, I will always mean in the sense of almost everywhere. Okay. But in the cases which are where it's a stronger convergence, where actually the functions converge to really the function itself, then I will explicitly say it. But if I don't say anything, it means the convergence is in the average sense, in the mean sense, is almost everywhere. Okay. So what does it mean almost everywhere? It means that this function converges to some function which may not be, I mean, which may not be this f. Right, exactly, but it should be, I mean, it may differ from f in a set whose Lebesgue measure is 0. So, for example, a countable number of points, okay, it may be different, okay, but that will be fine. I mean, from the point of view of this Lebesgue, I mean, integral, I mean, this L2 spaces, we in fact identify those two vectors. We don't consider them as two different vectors who differ only a countable set of points. Okay, they are the same states. So in this sense, but today we will see actually in this Weierstrass theorem that we can construct some things which are, I mean, there can be also convergence in a strong sense, in the stronger sense, where actually the convergence is to the function itself. So it's everywhere at every point. We will discuss today, but anyway, this was the main discussion of last time. Now, of course, all these discussions last time was on the was using this orthonormal basis, where it is clear that you don't need to choose orthonormal basis. I mean, you could have just chosen some other basis, right? After all, given this orthonormal basis, I can go to some other basis, right? Or vice versa, given a different basis, I can use this orthogonalization procedure to systematically start constructing orthonormal basis, right? This can be done at least for a countable set of basis vectors, right? In principle, I mean, you can keep doing. If it was uncountable, then of course you cannot even start doing it, right? But for the countable set of basis vectors, you can, in principle, do it, at least in theory. So all this discussion you can extend to just an arbitrary basis, not just an orthonormal. So the statement would be that I mean, if you are given a linearly independent basis, okay. Then you start proceeding with the orthogonalization procedure. You construct this basis, I mean the orthonormal basis, and if that basis satisfies this condition, okay, then the original basis that you started with is, I mean, original set of linearly independent vectors you started with is a basis. Okay, so this is the statement. So okay, so I mean it's so you can easily generalize it. Generalize this discussion to arbitrary basis, not just an orthonormal basis. This can be done. All right. So now let's start with today's topic. So in fact, what we will do is we'll explicitly construct some basis, a basis for the set of continuous functions. Okay. All right. So let's start. So this goes under the name of Weierstrass theorem. Okay. So the statement is what is the statement? Let me explicitly state the statement. So let's suppose f of x. Okay, the idea is the following: that if I take a finite interval, okay, a to b is a finite interval. I'm not taking all the way up to infinity. So these are finite. A and b are finite. So x is in a and b. Okay, and you consider an arbitrary function f of x in this interval, and further assume that f of x is continuous. Okay, so f of x is continuous for x in the interval a b. Okay, then you can approximate. We can approximate f of x to an arbitrary degree of accuracy by polynomials. By polynomials in x. This is very useful actually. In fact, in practice it's quite useful, because I mean, imagine we are given some function. This could happen, for example, you make some experiments, right? You collect data and you start plotting. Okay, you find some curve, right? But you don't know what is its analytical form of the curve, right? But what this theorem is saying, they can always approximate it to arbitrary degree of accuracy by some polynomial. Of course, the higher the degree of the polynomial will be, it will be more better accuracy will be. So it's quite useful from a practical point of view. Yeah.
Converge almost everywhere. Can we say that this sequence of function converge uniformly?
Converges uniformly.
Yeah. The sequence of continuous function converge almost everywhere. Can we say that this sequence of continuous function is converge uniformly?
No, that is a different concept, right? Uniformly convergence means that you can choose. You remember this convergence issue was always given an epsilon, you can find an n such that fn x. I mean, so for any epsilon, for any epsilon greater than 0, you can find an n. So there exists an n such that fn f, the distance between this is less than epsilon for all n greater than capital N, right? However, the point is that in general this n will of course depend on epsilon clearly, but in general it can also depend on x, right? So uniform convergence is a statement that when you can choose an n which does not depend on x. So that's a different concept. However, in this theorem we will show that it is actually uniform convergence for this Weierstrass theorem. Okay, that we can choose, we can find something which uniformly converges at all x's. We will see that. But this is a different concept. I mean, this has not so much to do with whether it's almost everywhere or not. I mean, even if it was sort of converging to even continuous function, right? I mean, suppose this function was also continuous, right? It may still be that it is it's not uniform convergence. No? So that can happen. Yeah. Sorry, repeat that again.
According to the fact that the set in which we choose our fn is complex.
Is complex.
Yeah,
It's complete.
Yeah. It means that all points are relation points. Because if you take a point, it means that
Sure. Yeah. If it's complete, then you can write. Yeah.
Then this is, by this definition, we can say that what my friend is saying is identical to uniform convergence.
But I mean, to me, uniform convergence is a different concept, right? It is to do with the how, whether, I mean, uniformly convergence means that at every point of x, it's kind of converges as rapidly as, so, right? Whereas when it is not uniformly convergent, it is like in some places it is converging fast, but in other places converging very slowly, right? That the kind of examples we discussed, I mean, some functions we discussed, right? I mean, so they're yeah. I mean, you have to, I think which was the example we, there was some example we discussed, right? Yeah. Sorry, which one was it? Can you repeat that? What was it? Yes. Yeah, nx over 1 plus n square x square, right? So here the problem was that near x equal to 0, the convergence was very slow, right? You have to go to too high an n to start seeing this convergence, right? So I mean, so here you had to choose this n, which was not only a function of epsilon but also x. This was the problem here. For x not close to 0, there was no problem. I mean, it was everything was converging very rapidly, but near x equal to 0, it was behaving in a very different way, right? No, these are two different concepts. You see, this converges to function 0, right? Everywhere. And 0 is a continuous function, right? So I mean, I'm saying that these are two different concepts. This is not uniformly convergent. Yeah. But actually the function is not uniformly converging, but nevertheless it is converging to a continuous function, which is a 0, right? But here we are saying that it is so the example here was the other thing, the step function we discussed, right? This was the sequence of functions which you can take to be just I think tan hyperbolic. Just let's take that tan hyperbolic nx, no, between the x going to minus, between x, say in minus 1 to 1, plus 1 if you wish. Okay, if you take these functions, this is I mean converging to actually the step function, which is not continuous, right? I mean here it is converging to a continuous function. So I'm saying that these are two different concepts. This is converging to a continuous function, but it's not uniformly convergent. Okay, here okay, it's converging to even and not a continuous function. So, yeah. Right. So this is a very nice theorem, because it says that, I mean, you can choose a basis of polynomials basically, because if you can approximate any function to arbitrary accuracy in terms of polynomials, then it's clear you can choose a basis as simply 1 x square, because then you can write as linear combination of this 1 x and x square, x cube, etc. Right. So that is a basis, not orthonormal basis, but it's a basis. Okay, so how do we prove that? Actually, proof will be pretty constructive. In fact, we'll explicitly construct the polynomials. Sorry, here. So, but before that, I need to prove a little lemma before proving this statement, and that is the following. I mean, it may not look that this lemma has anything to do with that, but it will be used. So the statement is the following, that if there is a delta which is between 1 and 0, okay, I just choose any number delta between 1 and 0, and consider such an integral a n delta. This is simply delta to 1 minus y square to the n dy. Okay. So this is the definition of the a n delta. You just take this in 1 minus y square to the n, integrated between delta and 1. So remember, delta is between 0 and 1. Okay. So somewhere it's like here is 0, 1, and delta is sitting somewhere here. So you're integrating from delta to 1. This function. Then this, what the lemma says is that then a n delta divided by a n 0, right? You just take a n 0 by definition is something which starts from 0 to 1. The integrals from 0 to 1. Just putting delta equal to 0. Okay. The limit of this as n goes to infinity, this is 0. Okay. This is the statement. It's not hard to understand why is that so, because well, first of all, let's look at the a n of 0. A n of 0 is what? Is just from 0 to 1, this integral. Okay. This integral is, I mean, one can explicitly work it out, but okay, this is an integral. But if you look at this integral, from where does the contribution come for large n, right? You see, when y, so y is between 0 and 1 here, right? Suppose you're looking at the region where y is away from 0, somewhere away from 0. So look at the region where y is greater than, strictly greater than 0. In that case, 1 minus y square is a number which is less than 1, right? Now, some number which is less than 1 and you're raising to the power of n, so it will become even smaller and smaller and smaller. And in particular, n goes to infinity limit, this will almost become 0, right? So the statement is that this integral gets basically the contribution from the region which is very close to y equal to 0. From everywhere else, the contribution will die in the large n limit, right? I mean, if you try to plot 1 minus y square to the n in this from 0 to 1, so this I am plotting this guy. At y equal to 0, it doesn't matter whatever the value of n is. This is just 1. 1 to the power of n is 1. So it will come here, right? But the moment you increase the y, this becomes a small less than 1. This number becomes less than 1, and raised to the power of n, it becomes even smaller, right? For example, suppose this was 1/10, okay? Then this becomes 1 over 10 to the power of n, right? And suppose n is 100 or something, is 1 over 100 zeros down. So it becomes very, very small. So this function is just going to become very rapidly, it will go to 0. I mean 0 meaning almost close to 0, very close to 0. Okay. So that means in this integral, really the contribution will come only from the region very close to 0, right? Everywhere else it goes to this function goes to 0, right? That is why you see now here when I do this integral, delta is some number here, some point here, right? So now if I take n larger and larger and larger in this region, this 1 minus y square to the n is very, very small, almost 0. Okay. So there will be no contribution. I mean, this will almost go to 0, right? This is the reason for expecting this to be true. But now we'll see that this is indeed the case. Okay. So the way to prove is again just take the, I mean, you want to prove that something is going to 0, the ratio of two things. So what you can do is you look at the upper bound for this, the numerator, and the lower bound for the denominator, right? So let's see. So first of all, a and delta. So we want to find the upper bound for this, right? So this is of course that. Now you see in this, I mean, after all, if in this range, y square is greater than delta square, right? Greater than or equal to delta square, right? I mean, and less than or equal to 1. Okay. So 1 minus y square is going to be less than or equal to 1 minus delta square. Since y square is greater than or equal to delta square, 1 minus y square is going to be less than or equal to 1 minus delta square, right? So I can as well replace, so this is going to be less than or equal to, actually strictly less than in fact, 1 minus delta square to the power of n dy delta to 1, right? Upper bound. I mean, because 1 minus delta square is greater than 1 minus y square, right? So, I mean, a and delta was that. Now, what I am saying is that 1 minus delta square to the n is bigger than 1 minus y square to the n, right. So, therefore, this bound is the upper bound. And now, this integral is what? This integral is 1 minus delta square to the n times 1 minus delta, right, dy. Well, but this is also less than 1 minus delta square to the n, because 1 minus delta is a number which is less than 1. So, if I replace this by 1, the result will be only bigger than that, right. So, you have an upper bound, which is this. A n delta is upper bound. Whatever it is going to be less than 1 minus delta square to the n. Okay. Now, for a n 0, we will try to find the lower bound, because this is in the denominator, right. So here the integral is this a n 0 is that, but notice that 1 minus y square, well, let us see, I mean y is greater than y square, right, in the range where y is between 0 and 1. I mean y is something which is less than 1, right, I mean greater than or equal to, let us say. At y equal to 1 this is equal, but if y is less than 1, y square will be even smaller, right. So, y is right. So, therefore, 1 minus y is going to be less than or equal to 1 minus y square, right. So, and since we are interested in finding a lower bound for this, so this is greater than a n was, remember, 0 to 1 minus y square dy to the n. So, therefore, this is going to be 1 minus y square is greater than or equal to. So, this is greater than or equal to, I just replace 1 minus y square by 1 minus y, right. So, you get here 0 to the 1 minus y to the n dy, this is right square. And what is that? That integral is simply is 1 minus y. I mean this integral is you can immediately perform, you know, this is simply 1 minus y to the power of n plus 1 divided by n plus 1 with probably a minus sign and the range 1 to 0, right. Okay, the upper limit it is 0, because at y equal to 1 this is 0, lower limit this is 1 to the n plus 1, which is 1. So, the minus minus cancels because the lower limit. So, this is simply 1 over n plus 1. Okay. So, we are finding that a n of 0 is greater than or equal to 1 over n plus 1. So, this ratio therefore, I mean, so let us look at this ratio. This ratio is going to be less than or equal to 1 minus delta square to the n divided by 1 over n plus 1, right. So, I can put this n plus 1 up there. So, this is same as n plus 1. Okay. And now you see that this is I mean in n goes to infinity limit, this is exponential behavior, I mean e to the negative, right. I mean, so maybe I should say it a bit more clearly. I mean this limit goes to 0 for the following reason. Let us write this thing, you see 1 minus delta square is some number which is less than 1. So, its logarithm is negative, correct. So, I can write this 1 minus delta square to the n as exponential of minus the modulus of log of 1 minus delta square. Okay. I mean, so this is a positive number. I took out the minus, because log of 1 minus delta square is a negative number. So, that is why I just to explicitly see this times n, right. That is what it is, right. I mean, call this thing, this some positive number, call this, I do not know, t, let us say. So, what we have is e to the power of minus t n. So, this expression is actually n plus 1 divided by e to the t n, where t is some positive number. Okay. Exponential, so as n goes to infinity, this is growing exponentially, whereas that is growing only linearly, right. So, in the n goes to 0 limit, it vanishes. I mean, exponential growth is much faster than any polynomial growth, right. So, is that clear? Which part is not clear? I mean, maybe, okay, let's write it down. So what did I do? I just wrote 1 minus delta square to the n as e to the power of minus modulus of log 1 minus delta square to the n. The reason why there is a minus is because log of 1 minus delta square is negative, is less than 0, right? Because log of 1 is, log of the argument which is greater than 1 is positive, log of 1 is 0, but log of some number which is less than 1 is negative, right? So that's why this is negative. So I just I write that as minus times the modulus of this. So that, and I call this as this some positive number. I call that as t. So therefore, this expression is n plus 1. I mean, this is e to the power of minus tn, right? Okay, I just rewrite that as e divided by e to the tn, right? After all, e to the minus tn is the same as that. So now this is growing exponentially to infinity as n goes to infinity, but that is only polynomial growth. So this grows much faster than that. So as n goes to 0 limit, this goes to 0. N goes to infinity limit, this goes to 0. Okay. That's what we wanted to prove. But the main reason is what I mentioned to you before. The intuitive reason is that this integrand for large n vanishes very rapidly in this region, right? The only place where it fails to be 0 is very close to y equal to 0, right? So, but that is captured by a n 0, right? So clearly the ratio, I mean, that's the reason why this is vanishing. Okay, so this will be used in the proof of the Weierstrass theorem. Okay, I can erase all this now. Okay, so let's so suppose I'm given an interval a to b, and I'm given some function f in this, right, continuous function. Now it turns out to use this lemma, it is convenient to change this interval, okay, but that you can always change by changing the coordinate system, right? Redefine some new variable, and that new variable you can put it in any interval you want, right? So for example, you can choose, so I will, by making a linear transformation on x, I can make this to a interval sigma to 1 minus sigma, where sigma is some number between 0 and half. So this interval, I will bring it to something like this. So here is my 0, here is 1, and this is some sigma. Sigma is between half and 0. This is my half, right? So sigma to 1 minus sigma. So this will be my range. This you can always do by change of variable. For example, let's write it like this. X prime equal to 1 over b minus a times x minus a times 1 minus sigma plus b minus x times sigma. Okay. If you do this, so you can see indeed when x equal to a, the lower limit of the interval, this vanishes, and this becomes b minus a, b minus a cancels, and you get x prime equal to sigma, right? So the lower limit here becomes sigma, and the upper limit is when x equal to b, this vanishes, and then this becomes b minus a, which cancels, and you get 1 minus sigma. So upper limit becomes 1 minus sigma. This is it's a convenient way of, you can always do that. There's no problem. You can, given any interval, you can, by suitable coordinate transformation, you can go to another interval. That's always possible. And in fact, here we are even doing a linear transformation. This is a linear transformation in x, right? I mean, it's only linear terms appear in x, not quadratic. I mean, the x and 1, I mean, constant and x, that's all. So the linear polynomial, linear function. So it is sufficient then, I mean, if I can prove Weierstrass theorem here, that in this range, any continuous function here I can approximate by polynomials, right? Then it's okay, it also goes through here, because I just have to go back to the, from x prime, I just go back to the x coordinates, right? Wherever you see x prime, just replace it by this. So you will get again a result for this. So it is sufficient to just look at that, this problem. Okay. So here I am given some function. So we'll take the so f is defined. So I might as well, I will not drop x prime and so on. I will just call it x, and I will just take the interval x to be inside sigma to 1 minus sigma, where sigma is between 0 and half. Okay. So I will just do it here, because then you can translate it to any other interval. That's not a problem. Okay. Now, so here is the thing. But what I will do is again a technical trick. It's nothing more than that. So here is some function, whatever that function is, some continuous function is given here, which is defined between sigma and 1 minus sigma. But I will extend this function all the way from 0 to 1. Okay, in any way you want. I mean, you can just define in any way extension. Okay, but it should be continuous, and it should be not. It shouldn't go to infinity, right? Okay. So as a simple example, you can just extend it like this. So here is my function, which is given to me, whatever the continuous function is, and now I extend. Just take a straight line here, and straight line there. So in all this region, I take the value of the function to be the same as the value of function at sigma. Okay, and all of this region, I take the value to be the same as the value at 1 minus sigma. But this answers, the result will be independent of the way you extend it. Okay, this is just a technical tool in between, intermediate step. So I will define f of x. So here x is inside, right? But I will define now this function f of sigma, f of x. So I don't know, let's call it f tilde of x, f of 1 minus sigma for x between less than sigma and greater than 0, okay, greater than or equal to 0. And this is between sigma, x between sigma and 1 minus sigma. And this is for x greater than 1 minus sigma, less than 1. Okay. So this is what I have shown here. So I've extended here, just take the value here and just keep the same value, and here extend. So now you see this f tilde is defined between 0 and 1, 0 and 1 all the way. Okay. So f tilde x is defined for x between 0 and 1. Okay. Okay, so now, as I said, this proof, that the theorem will be proven by actually giving you a formula for this polynomial. Okay, so the polynomial, this will be the polynomial. So we write down a polynomial 2n degree, even degree, 2n degree x, and this is simply defined as 1 over 2an0. An is what appeared in the lemma, that same an of 0, and the integral 0 to 1 of f, say z. This z is real. I mean, don't think of it as complex. It's just, I don't know, maybe I should call it something else, y. F of, because z one always thinks of as complexness. So f of y, and 1 minus x minus y square dy to the power of n dy. Okay, where I will take in this formula, I will take x between sigma and 1 minus sigma. Okay. I mean, the reason why I have needed to extend this definition of, so this is f tilde, let's say, this is f tilde. I had to define, because y is going from 0 to 1, okay, and f tilde is a function of y. So you have to somehow extend That's why I needed to go through this technical thing. Although eventually in the end it will not matter. Okay. In the end it will not matter because in this formula the x I am keeping it to be between sigma and 1 minus sigma, and you will see that the entire contribution will come from the region where y is very close to x. That's the only region where it will contribute. So yeah, okay. So now, so we want to, so this is what? This is a 2n, y is 2n, because look at this, this is a polynomial in x clearly, right? You can open this bracket, this is 1 minus x minus y squared whole to the power of n. So the highest power of x that will appear is the x squared to the power of n, x to the 2n, right? And then the lower powers. So this is whatever it is going to be some 2n degree polynomial with various coefficients. Coefficients will be just this result of these integrals. And now what we'll show is that this polynomial will approximate my original function to an arbitrary degree of accuracy provided for larger and larger n, right? Okay. So okay, let's just start from this, and let's change the variable. This is x minus y. So let's change the variable. Say y. Let's put y equal to x plus now t. Let's say t. I don't want to use a z, not to. So x plus t. So this integral. So this is the same as 1 over 2a and 0. But now look at the range. When y is 0, t is minus x, right? So this will start from minus x, and when y is 1, t is 1 minus x. That's that. And then you have f tilde of x plus t, okay, and then you have 1 minus t square, right? Because y is equal to x plus t, x cancels, there's a minus t, but anyway, I'm taking the square, so it becomes t square to the power of n dt. I mean, dy is the same as dt. X is fixed, right? X is something fixed. All right. So now let's do this. Let's split this integral. After all, minus x to 1 minus x, I can write it as minus x to some minus delta plus minus delta to plus delta, and then from plus delta to 1 minus x. For where delta is something small, so how do I define delta? So delta is defined in the following way, that yeah, this I don't know. That, so how is delta defined? So delta is defined as by this equation, that f of x plus t, let's say, minus f of x absolute value is less than some epsilon divided by 2. Epsilon is some small number. I mean, this is the epsilon which appears in the limits. So for arbitrarily small epsilon, but something non-zero, positive, but arbitrarily small, for all t in between minus delta. So t is between less than delta. I mean, t is between minus delta to plus delta. Okay. This is, I mean, that such a delta exists. You are guaranteed. Why? Because I know, you remember this function f is continuous, right? You remember already starting point was in the definition, in the theorem of the Weierstrass, you are taking a continuous function f. Okay. When it is continuous, no matter how small epsilon you choose, there always exists an interval delta such that the difference of the f at any point in psi interval from the f at x is less than epsilon by 2. That's just from the continuity, right? You remember this? I mean, this is the definition of continuous functions. I mean, basically, just saying that as you approach, I mean, as you take t to 0 limit, I mean, so this function, the difference between the value of the function here and the value of the function at t equal to 0 will go to 0. That's what the meaning of continuous function is, right? So delta is defined like that. So I choose that delta, okay, which enters in this continuity equation, Okay. And I choose, I split this integral in terms of these three integrals. Okay. And what will happen, as you would expect, that the entire contribution will come from here, from this little integral, and none of those things will contribute. Okay. But we have to show that actually. Okay. So let's first do this this part of the integral, which will be really give the non-zero answer. Okay. So I do this integral minus delta to plus delta f of x plus t 1 minus t square to the n dt. Okay. I mean f till it doesn't matter because see x I'm taking to be in this region, but in that region f tilde was the same as f. Okay. So I just replace this f. Okay, I do this. But then let's rewrite this as integral of fx. I mean add and subtract fx. No, I mean so let me write it like this. So minus f of x plus f of x. I'm just adding and subtracting. So I do nothing, right? 1 minus t squared to the n dt. Okay. Now this difference is bounded by epsilon by 2. So I split into two parts, two integrals. One integral is this, another integral is that. But this, for this integral, this does not depend on t, so I can take it out, right? So let's look at that integral first. So this is simply f of x, and then this integral minus delta to plus delta or 1 minus t square to the n dt, right? But this is even function of t, right? So this is the same as 2 times 0 to delta, right? I mean minus delta is the even function. I mean minus delta to plus delta is the same as 0 to delta and multiply by 2. And furthermore, 0 to delta I can write it as 0 to 1 minus delta to 1, right? Okay. I mean 0 to delta, I do the full integral 0 to 1 and subtract from that the result of delta to 1 integral, as same as that. But this you recognize, this is simply a0, an 0, and this is an delta from the previous definition, right? So what we are finding is this is the same as 2fx times an 0 minus an delta. That's the result of this integral. I mean the middle integral. But remember, I have to also divide by this 1 over 2 a n 0 here. So really I have to divide this by 1 over 2 a n 0. So there is a 1 over 2 a n 0. So this 2 cancels. This a n 0 goes out, and then what is left over is here is a n delta divided by a n 0. Okay. And you see you are already you obtained the answer, because the lemma we already shown that n goes to infinity, this vanishes. So you are getting back this function f of x. Huh? Yeah.
When you see that the delta function is defined by this, then at that integral you removed f of x. Why is f of x plus t minus?
No. At the moment I'm just doing this part. Now I have not done this yet. Yeah. Now the next will be I will do that. Okay. But you agree that this part of the integral is that. Huh? So now the remaining part here. So there is this piece. So sorry, I should write it like maybe. So what shall I write? So let's call this term number 1, and that is term number 2. Huh? So the term number 1. This is term number 1. So term number 2 now. Well, this is simply 1 over 2 a n 0 minus delta to delta, and let's take the absolute value of term 2. So this absolute value will be less than or equal to the absolute value of that, right? F of x plus t minus f of x times 1 minus t squared to the n. I mean this is always positive, so absolute value doesn't do anything, dt. but this guy we said is less than epsilon by 2, right. So therefore, this expression is, oh, I should, okay, this you remember, I just split this integral into 3 terms, and I'm still looking at that only, the middle one. So this is less than epsilon by 2, this is less than epsilon by 2, I take out epsilon by 2, so you get here epsilon by 2, 1 over 2a and 0, and then minus delta to delta, I mean this goes out, then that integral is the same as that, right, original thing. So that gives you 2 times a and 0 minus a and delta, for the same reason. I mean this, in fact this has come out, I have taken out epsilon, right, epsilon by 2. This was less than epsilon by 2, so I write it epsilon by 2 and take it out. Then what is it? The result of this integral is just that, but that's even, so you get a 2 times 0 to delta, and 0 to delta is same as 0 to 1 minus delta to 1, so that's that. So this 2 cancels, and okay, that's the answer. So once again I can put this inside here, so you get here the same thing, 1 minus a n delta divided by a n 0. Okay, so the second term is less than that, the first term is equal to that, and now we have to worry about these last 2 terms. Okay, so let's look at these last 2 terms, and maybe I just do it here. Okay. Right. So the idea here is again, I mean, to take the bound. I mean, after all, this is a continuous function. So continuous function, there is always you can look at the maximum value. I mean, again, take the absolute value of these things. Absolute value of minus x to minus infinity, minus delta, and then plus delta to 1 minus x, plus delta to 1 minus x. Okay, and of this integrand. Okay, let's f of x plus t, 1 minus t square to the n dt, and plus delta to 1 minus x, f of x plus t, 1 minus t square to the n dt. Okay, and let's take the absolute value of this thing. Now the point here is that the absolute value of, I mean, this f is a continuous function in this range. It is bounded. Okay, so it will be, it has some maximum. I mean, it will be something less than some number, right? Whatever the maximum value of f is in that region, in this domain from 0 to 1. Okay, whatever that it is, it will be that maximum value, right? So this is going to be less than or equal to max of f. Okay. Absolute value, max of f. Oh, sorry, I forgot about 1 over 2a n 0 here again. Max of f divided by 2a n 0. Okay, and then the result of this integral, minus x to minus delta and delta to 1 minus x. Okay, so this is simply the integral 1 minus t square to the n. So let me write it like this: minus x to minus delta plus delta to 1 minus x of the integral 1 minus t square to the n dt. This is a bound, because you say what the idea is this: we already got this answer. I mean, what desired answer we already got from that. Now we want to show that the rest of the things don't contribute. So we just look at the upper bound and show the upper bound goes to 0, right? So this is the upper bound, and you get this. Now again, I'm interested in upper bound, so I might as well replace this by minus 1. Remember, x is between, I mean, x is less than, is not, I mean, x is between sigma and 1 minus sigma. Okay, so if you replace this by x equal to 1, I mean this range, it doesn't matter, right? Because you're only increasing the range of integration, and in that range of integration, this is always positive. Okay, is that clear? I mean, I have a positive quantity and I'm integrating from something to something. Okay, now if I increase the range of the integration, the result will only be bigger than the original result, right? So I might as well put here, since I'm looking at the upper bound, I might as well put this as -1 here. I'm increasing the range of integration. Similarly here, there's 1 minus x, but just make it 1. Again, I'm increasing the range. So whatever the answer I will get will be even more than what it was before, right? Okay. But this is again even function, so I can as well, this just becomes delta to 1. So it's 2 times this answer, 2 times this result. But that is by definition a and delta, right? So this whole thing is what we are saying is, so these two, what shall I call now? Third and fourth term. This is third and fourth term. Our conclusion is the absolute value of the third plus fourth term is less than or equal to max f divided by 2a and 0, and this thing was simply 2a and delta, right? So now we can combine all of these things, and you find that so we find, okay, I can just combine now everything. So this was the first term in the middle. So this whole thing was the middle one, which we split into 2 terms, 1 and 2. First term gave me already the fx. The second term I have a bound, upper bound, and the third and fourth terms, the sum of third and fourth terms, again I have an upper bound. Okay, so I put them all together. I think I can erase this now. Okay. So we find this whole thing was Pn, P2n, right? P2nx. So we are saying that P2nx is equal to f of x minus f of x times a and delta over a and 0 plus, okay, this is epsilon by 2 times that, but obviously I can replace this by 1 because anyway this is something, I mean this number is less than 1, right? And since I'm only interested in upper bound, I can just forget that, right? Okay. So some that so let me take fx on the other side. Huh? So Pnx minus f of x, and let's take the modulus of this. Okay. So then we are saying that that is less than or equal to modulus of this whole thing. Okay. Modulus of this plus epsilon by 2 plus this quantity, which is max f times a n delta divided by a n 0. Right? That was the sum of the third and fourth. This 2 cancel, and you just get this ratio, a n delta divided by a n 0. Okay. I mean, so now in the large n limit, you can okay, this is the same as that. I mean, you can even put it like max f. This is max f, and that is f. Huh? So I can as well replace it by max f because I'm looking at upper bound. So even this I can put them together as 2 times that. And now all you need to do is to just choose a sufficiently large n, because this, remember, this goes to 0. So sufficiently large n such that this whole quantity is less than epsilon by 2 for sufficiently large n, for large n. So choose some large enough n such that this whole quantity is less than epsilon by 2. Then we see that the difference is less than epsilon. Okay. So this is where the lemma is used. Lemma is used in this thing, taking the limit. This limit, goes to 0. Is that clear, or is it unnecessarily complicated? I mean, the main point of this was that really the integral is getting contribution only from t equal to 0 point, near t equal to 0, because that's where it's 1. For away from t equal to 0, this is a smaller number, and that to the power of n becomes very, very, very small for large n. And near t equal to 0, basically f of x plus t is the same as f of x, right? and that's why you get back f of x. That's the main reason. That's the reason why only this part of the integration contributes, because this is where t equal to 0 lives, right? And all these integrals don't contribute. I mean, they are all going to 0 in this limit. I mean, the result, sum of these two was basically that, which went to 0 in the n goes to infinity limit. That's the main reason. But okay, this is all just doing precisely, I mean, to working it out, estimating, putting limits and things like that. But the main reason is just that. Okay. But you see, this is a strong, in the strong sense. It is not in the sense of, you know, on the average or on, I mean, on almost everywhere. This really, I'm talking about at every x, the difference between this is less than epsilon, and it's uniform convergence. You see, it's uniform convergence, because the right hand side doesn't care about x. Right? It's a completely uniform convergence. At every x is converging rapidly, the same rapidity. So it's a much stronger result. I mean, of course, the only thing is that it's for continuous functions. For continuous function, you can find this. You can approximate it to arbitrary accuracy by polynomials, provided you take larger and larger degree polynomials. In practice, of course, you don't do that. I mean, if you put it in the, if some curve is given to you, you put it in the computer and you try to, you know, you look at some, you allow some possible error, and you know, it'll, I mean, it'll maybe third order or fourth order, fourth degree or something like that. You stop there, more. You'll get pretty good approximation for reasonable function, unless the functions are really oscillating very rapidly or something. Okay, although this was proven for the continuous function, but it's also clear that you can extend it to all the functions in the L2 space. Why? Because of the statement I made before, that any function in the L2 space can be written as a limit of a sequence of continuous functions. Okay, and since continuous functions you can approximate by polynomials, therefore also, so every element of the sequence you are approximating by polynomials, right? So therefore also in the limit, whatever the limiting function is, that can also be approximated arbitrarily accurately by this. But that will be not in the sense of not pointwise thing, but that will be in the almost everywhere sense, right? Because there you are using the distance functions actually. Okay. I mean, the essential point is to use the, so what we are saying is that, so suppose that some f is given, which is an element of L2 W space, okay, and then so then we know that there is a sequence of continuous functions whose limit is this. Okay, so you have f1, f2, fn, etc., etc. And this is converging to f, but in the sense of the distance, right? So we are saying that the row of f with fn. I mean, since we are talking about functions, I usually forget to put this bracket notation, because it's really functions now. But okay, if fn is less than epsilon for n sufficiently large, n greater than some capital N, right? But it's a distance function. Okay. Now, if you, but on the other hand, for each of this fn, I can find some polynomial, let us say 2m, okay, and I put here n to indicate that this is approximation for the fn, for this nth function, right? For nth function, I can approximate by some polynomial, 2m polynomial, such that fn minus pn 2m absolute value is less than epsilon for sufficiently large m. For any fn, so if you can choose sufficiently large m so that this difference is less than epsilon. And then you use a triangular inequality. So I mean, of course, if the difference is less, then it's also true that if we compute the rho is also less than epsilon. I mean, some number, small number. Is that clear? Is that clear that, I mean, if this is less than, I mean, this can be made arbitrarily small, then the distance between these two functions is also can be made arbitrarily small. Because after all, the distance is taken by simply taking the, I mean, distance square is just taken by taking the mod square of this and integrating, right? That will be, I mean, since this is less than epsilon, the epsilon you can take it out. You can find a bound of it. Epsilon square you can take it out, and then the epsilon square times interval, the length of the interval, right? That's what you get, or the integral of the weight function, which is some finite number. So that will also be true. This is less than f. And now you use a triangular inequality. So I mean, rho. But what we are interested in is approximate f by some polynomial, right? So if you take the triangular inequality, rho of f p2m n is less than or equal to the sum of these two. That's a triangular inequality, right? But each of them is less than epsilon, so this will be less than or equal to 2 epsilon. Okay, so you can make it arbitrarily small. Epsilon goes to 0, right? So yeah, so I mean, so this extends to the full L2 space. That in the full L2 space, for finite interval, AB is finite interval, you can approximate these functions by polynomials. For continuous function, it's really not in the sense of almost everywhere. It's really everywhere. Huh? But for non-continuous functions which are in the L2, they will not be everywhere, but almost everywhere, because there we are now relying on the distance function, right? Which is defined through the integrals, through the Lebesgue integrals, right? So okay. Now let's see if I can. Is there any question on this? I mean, this is just a basis, not orthonormal basis yet, right? Orthonormal, we are not even defined, we have not even used the weight function anywhere here, right? This is complete, because we are not interested in the computing distance functions. We're actually looking at really the value of the function at each point, right? So that's why we never needed the weight function so far in this discussion, right? But so what we are guaranteed is that you can choose a basis as a polynomial basis. So for example, 1, x, x square, x cube, etc. Because any continuous function I can expand in terms of this basis functions. But they are not necessarily orthonormal, right? In fact, that whole question of orthonormality will depend on the choice of W. Okay. So the next step is actually to construct orthonormal basis. But we will not follow the standard procedure, because that would be impossible to, this is the infinite dimensional spaces, you can, so there's a trick, and that is a trick that we will go through. So idea is now to construct orthogonal polynomials. Actually, when we construct orthogonal polynomials, we'll find that actually we can even take the range a, b to infinity, okay, provided you impose some sufficiently sufficient fall off conditions on W, the weight functions. They should fall off sufficiently rapidly. I mean, exponentially, basically, should fall off. Okay. In that case, you can even extend to the infinity. I will start this discussion today, but then we will discuss the details of it next time. Okay. So there is this formula. There is something called generalized Rodriguez formula. Rodriguez formula. Okay. This formula will give you a certain class of orthogonal polynomials, not all the class. But it will give you quite important classes. For example, it will give you Legendre polynomials, Hermite polynomials, Laguerre polynomials. Everything will follow from there. But this is not the complete Yeah, many things you cannot find with this, but it's a very elegant method which just gives you in one shot a huge class of polynomials which appear very frequently in physics. So, we will discuss this. So, idea is the following. Well, I mean, let me give the definition. So, it's defined like this: Cn, let's define something like this: Cn of x is equal to 1 over w. W is a weight function. So, this we are looking at the so this x's will be always in some range a to b, okay, and there is a weight function x. There is a weight function. One over wx dn over dxn n derivatives of w times s to the n. So, consider such. So, these are all functions of x, w of x and sx to the power of n, where n starts from 0, 1, 2, etc., all integers. For n equal to 0, you see, you can immediately see it just gives you 1, right, because n is equal to 0, so there is no derivative. This n is 0, so no s. So, you just get w divided by w, which is 1. So, that is the first term. I mean, in this you have 1 x, x square and so on. So, this is the first term 1. Okay. But so what are these w, what are the conditions? But I mean, we have to specify some conditions on w and s. So, first condition is that C1 of x should be linear. Linear in x. I mean, it's not guaranteed, right? From this expression, if you take generic w and s, if you compute even first derivative, there's no reason why it should be linear, right? So, this is we are imposing a condition. So, we are saying that w and s should be chosen in such a way that C1 should be linear. Okay. Second condition, that s of x is a polynomial of degree, polynomial of x, I mean, degree less than or equal to 2. So, at most quadratic, s is at most quadratic in x. And third has to do with the boundary conditions at the interval, because boundary conditions will be important, right? I mean, after all, when you are going to talk about orthonormality and so on, you have to impose some boundary conditions. I mean, it will turn out, because we will use this, we'll do a partial integrations many times, because there are a lot of derivatives, right? In order to evaluate various integrals, we'll start doing partial integrations, and when you do the partial integration, you'll get boundary terms. So, you need to impose some conditions on the boundary, okay? And those conditions are that w times s, w of a times s evaluated at a is equal to 0, as well as the other point, and w at b, s at b equal to 0. So, at both the endpoints, the product of w and s vanishes. Okay? W times s should vanish. This is the condition. And of course, the usual condition for w, that w is a weight function, so it is positive, is integrable, etc. I mean, so the usual condition for the w is positive, and the integral of a to b wx dx should make sense. I mean, it should exist. It should be less than infinity, should exist. There are usual conditions. So, but apart from that, there's this boundary condition I have to satisfy. Okay. Now, with these three conditions, one can show that these are actually orthogonal polynomials. These C and X are orthogonal polynomials with weight function W. Okay. So, I will go through that proof today, but then we will analyze these conditions next time. Okay. We will analyze what does it mean. I mean, we will try to find the solutions for, because remember, we have to choose W and S such that this is satisfied, and we will find there are only some very few choices of W and S. Okay. But those choices already give you a large class of functions. Now, today what I will show is that using these conditions, so assuming that W and S, I have found W and S will satisfy these conditions, okay, then the resulting CNs are orthogonal. Okay. That is what it will show. Okay. So, to prove this, we need to first look at obtain some what do you call kind of lemmas, let us say. So, first thing is first thing is to prove the following. This will be used in the actual proof finally.
Is there a reason for choosing W, a polynomial of degree
S, not W, S, I mean, it will enter in the proof. Yeah, correct. I mean, the proof will not work for S if S is higher than quadratic. Okay, we will not be able to prove that the C and X is orthogonal to each other. So first statement we want to prove. So lemma 1, let's say, is to prove that if you take m derivative, I mean, we need to know some properties of this, how the derivatives act on this. And so we are looking. So that's one of the property here. Times acting on W times s to the n. I'm not going to put this x inside. I mean, it's clear these are all functions of x, right? So I will not. Times any polynomial of degree less than or equal to k, a polynomial again of x. This everything is a function of x. So this notation means is a polynomial of degree less than or equal to k. So highest possible power is x to the k, not more than that. Okay. So this is equal to w s to the n minus m. So you see the m derivative. So this n reduces to n minus m, and at the same time this polynomial goes up to k plus m. So this is some polynomial of degree less than or equal to k plus m. Okay, this is statement. So how does one prove that? So we prove this using these conditions. Using these conditions. Actually, just the first two conditions, because this has nothing to do with the boundary condition. Just the first two conditions, we should be able to prove it. Okay, first let's look at the analysis condition. C1 of x is linear in x. So let's see what is C1 of x. I mean, so C1 of x is simply 1 over w d by dx of w acting on w times s, right? From this n equal to 1. Let's open this up. So you get here dw by dx 1 over w times s plus ds by dx, right? When this derivative hits there, this w cancels, right? So that's the term. Okay. So this can be rewritten okay, so I can just rewrite this in a certain way. So what it says is s dw by dx is equal to w times c1x minus ds by dx. Right? Okay, I just brought this. I brought this on this side and multiplied by w. So you get that. The important point is that s is at most quadratic. So ds by dx is at most linear in x. And C1 is also linear. So this whole thing is linear in x. So what we are saying is that s times dw by dx is w times a linear function, at most linear function. Okay. Okay. So let's now open this up. Let's look at first. Let's start by induction. I mean, just by first, let's take one derivative, m equal to 1. So let's just take d by dx acting on. So m is 1. W s to the n p less than or equal to k. Okay. So what is this? This is let's open this up. So this is d by dx, dw by dx, s to the n p less than or equal to k, plus w times n times s to the n minus 1 ds by dx p less than or equal to k, and finally the derivative hitting the d by dx, the polynomial of degree less than or equal to k, right. There are 3 terms. Now, here I use, so I can take out, I mean, yeah, here of course I am assuming that n is greater than 1, right. Okay, otherwise it's nothing, because for sure m is going to be less than or equal to n, right. Okay, at least, so here I am assuming that n is greater than or equal to 1. Okay. Because this is otherwise doesn't make sense, n minus m, right. Okay. And m is less than or equal to n. Okay. That's what we are looking at. So since n is greater than or equal to 1, at least there is one power of s, right. I mean, I can write this as s times s to the n minus 1, right. And then s times dw by dx is that, so I can replace this. So you get here, what is left over is s to the n minus 1, p less than or equal to k, and then you have a w, and I'm using this now, right, times c1x minus ds by dx. Okay. And then you combine with that. So this I can combine together. Okay, let me write separately. Okay, this is this piece, just the first piece. Then I add to that. So you can see what happens. That term is the same as that term, right? Except instead of minus 1, there is an n here. Okay. So when I add this up, this simply becomes plus n minus 1 times ds by dx. So I have taken care of both the first and second term. Okay. And finally, the last one is this plus w s to the n dp k over dx. Now, w times s to the n minus 1 is a common factor everywhere. So let me take this out. So this is equal to w s to the n minus 1 p less than or equal to k times c1x plus n minus 1 ds by dx, and w s to the n minus 1 I take from there, you get here s times dp less than or equal to k over dx. Okay. Now, that's what we want to check, right. So you see, if for m equal to 1, this is I'm computing the left hand side, and what we want to show is that this is w times s to the n minus 1, m equal to 1, right, s to the n minus 1 times a polynomial of degree less than or equal to k plus 1, right. Now, w times s to the n minus 1 I already got here. So all I want to show is that this is something, is a polynomial of degree less than or equal to k plus 1, right, which is of course true, because you look at this first term, this is polynomial of degree less than or equal to k, and it's multiplying something which is linear in x, right, because c1x is linear by the first assumption, and this is s is at most quadratic, so this is linear, so this whole thing is linear. So this is at most of a degree k plus 1, right. Similarly, this one is degree k, so you take a derivative, is degree k minus 1, s is quadratic, so once again is degree k plus 1, right, maximum degree k plus 1. So you prove that for m equal to 1, but then you keep taking more and more derivative, right. If you take now a derivative of I mean of this side, so right, I mean what I'm saying is that now if you take, so we proved already that d by dx of w s to the n p less than or equal to k is equal to w s to the n minus 1 p less than or equal to k plus 1, right. Now take one more derivative. So this is this derivative here, right. But then this is already proven for, because this is m equal to 1 case, but now choose n, instead of n you put n minus 1, okay, and instead of k you put k plus 1, and I again apply this statement for n equal to 1. So you find this becomes w s to the n minus 2, because you see already in the first step this reduced by one step, right. Now when you do one more derivative, it's going to reduce by one more step, n minus 2, and this is going to increase by one more step, k plus 2, and so on. You keep going. So what the conclusion is, the number of derivatives you put, that many steps it goes down, this power, and that many steps it increases here. This is the way. Okay. So that's the first lemma. Yeah, second lemma we need to prove. As I said, we'll be using a lot of partial integrations in this, proving the finally proving the orthogonality. But in order to do that, we need to control the boundary values. What happens? So there is a. Is there any question on this part? Is it any question? It's pretty straightforward, right? I mean, just follow the standard. Just take derivative of term by term. Use the condition of C1, the linearity of C1, and quadratic nature of S, and then it follows. Okay. Now we go to the second lemma. What it says is that yeah, okay. I mean, yeah, I'll come back to that. What it says is that dm by dxm acting on ws to the power of n. Okay. So for this, I have taken this polynomial to be just 1. K is equal to 0. So just 1. Okay. This for m strictly less than n. I mean, this was true for even up to m equal to n, m less than or equal to n. But now I'll take m strictly less than n. Then the statement is that this term, this is equal to 0 at x equal to a and x equal to b. Okay. That means that the n points this vanishes. That is almost immediate because what will you get? Just use that lemma, right? For the special case where this polynomial was 1, I mean the k is equal to 0, that means, right? 0th order degree polynomial. So you immediately find that this expression is the same as w s to the power of n minus m, okay, and then some polynomial of degree less than or equal to m, right? Because k is 0. That's what you find. But from the third condition, you see n minus m is since m is strictly less than n minus m is greater than or equal to 1, right? So you always have a ws term, and our third condition was that w a times s a is 0 and w b times s b is 0, right? So this will be 0 always. No matter what this polynomial is, doesn't matter, because I mean I can take out w times s. This is w times s to the power of n minus m minus 1 times the polynomial less than m. Okay. Well, when you evaluate this at a and b, it will be something, but it will be some finite number, because after all these are just polynomials, right? There will be some finite number, but the point is that w times s vanishes at a and b by our third assumption. So this vanishes. Yeah. So now we are ready to prove this statement. One thing I want to just look at, if you look at this expression and take m equal to n and say this polynomial is k equal to 0. If you take, so because this is all the way up to m equal to n, right? So if you take that, then the right hand side becomes w n equal to m, so this disappears, and you just get m equal to n, so nth degree polynomial, right? Because k is 0. But the Rodriguez polynomial Cn was defined by this quantity, so Cnx was 1 over w times dnx by dxn ws to the n, right? This was what it was, right? So now applying this lemma for k equal to 0, what this says is that this is w, but that w cancels with 1 over w. So this is some polynomial of degree less than or equal to n. That's what it says. Because the s disappears, right? S to the n minus m, n equal to m, so this disappears. So you just get that. So that is why, I mean, this is the nth, at most nth degree polynomial. Okay, we will now show that actually it is nth degree polynomial. In fact, not just, I mean, meaning x to the n term is not vanishing. We'll show that now. Okay. So finally we are in the last step, and then we'll stop last part of this. So now we will show that Cnx times Pmx Wx dx from A to B is equal to 0 for m less than n. So we are saying that any polynomial of degree less than n, so less than or equal, I mean m is less than n, right? For any polynomial of mth degree where m is less than n, it is orthogonal to the Cn. Okay, that's the first step we'll show. Well, to do this, let's substitute this Cn here. So when you substitute that, this w will cancel with that w, right? And what you're left with, this is the same as A to B dn over dxn acting on w s to the n times this polynomial Pm. Note the w has cancelled. That is important. W has cancelled. And now I can just start doing partial integration, right? So when I do the partial integration, so let's take the first one. So there will be boundary term, right? So the boundary term will be, so let's take the first one. So I'll get here d by dx of the whole thing, dn minus 1 by dxn minus 1 acting on ws to the n times Pm, times Pmx. This I can rewrite as that minus dn minus 1 over dxn minus 1 ws to the n times d by dx acting on polynomial m. Okay, right? This is just I'm rewriting that because if you take this derivative, this acting on both this factor and that factor, when it acts here, it gives you this, right? When it acts here, that cancels with that, right? That's just the usual total partial integration. I think. Yeah? Okay. Now the point here is that this, when I put it in here, is total derivative, so only boundary terms will contribute, right? But boundary term vanishes because of that lemma 2, because you remember for any m, any number of derivatives when it is less than n, it vanishes at the boundary at the endpoints. That was the lemma 2, right? So this will vanish, boundary term will vanish, and you get that. And you keep doing it. Next time it will be even better because it will be even less power. So, right? So all the boundary terms will vanish, and eventually you will just get this is equal to minus 1 to the n, because every time you do a partial integration there is a minus sign, and you are doing n times. So there's a minus 1 to the n, A to B, ws to the n, dn by dx n Pm x dx. But this is 0 because we are saying Pm is a mth degree polynomial which is less than n, m is less than n, and I am applying n derivatives. So it vanishes because this is the highest power x to the m, right? And I have n derivatives, so it will vanish. So this is 0. Okay. So you see, I've used the boundary conditions very crucially, right? So Cn is orthogonal to any polynomial of degree m. But you see, we already said that if I take instead of Pm, if I had replaced this by Cm, we already said the Cm is some polynomial of degree less than or equal to m, right? So Cn is orthogonal to Cm. Okay. If I take two different C's, Cn and Cm, one of them will be bigger than the other one. Either n is bigger than m or m is bigger than n. Either way, it is 0, right? So we have proven Cn and Cm are all orthogonal to each other. Okay. Finally, I just need to prove that you remember we said the Cnx is a polynomial of degree less than or equal to n. But now I want to show that actually the x to the n coefficient is not vanishing here. The Cn does contain x to the n term, so it's really degree n polynomial. Okay. And that can be shown in the following way. Well, in general, I mean, what this is saying is that Cnx is some coefficient, let's say a times x to the n, say a n x to the n, plus a polynomial of degree n minus 1, right? It may happen that a n is equal to 0, in which case this polynomial will be less than n, right? So we want to show that this coefficient a n cannot be 0. Right? So let's take now the square Cnx times Cnx, so Cnx square wx dx, a to b. This integral is certainly not 0 because it's a norm square of this vector Cnx, right? And Cnx is not 0, so this is certainly greater than 0. On the other hand, I can rewrite this as Cnx. One Cnx I keep as it is, and the second Cnx I write it like this. A to b dx. Yeah. Now this term vanishes from because of that, right? We said that for any any number which is less than n, and this is n minus 1 degree polynomial, so Cn is orthogonal to that. So this result is simply equal to a n times a to b Cnx x to the n dx. And this is strictly greater than 0, so it implies that a n is not 0, a n is not equal to 0, and furthermore this integral is also not vanishing. So in particular a n is not 0. Okay. Therefore, yeah, so this is the Cnx is really nth degree polynomial, not less than nth degree. So this is the, yeah. I think I'll just stop today here, and from next time I will then analyze those three conditions and try to see what kind of W and S can satisfy those conditions. And then we'll find there are basically three different classes. Okay. And those are, one of them is Hermite polynomial, there is, I think there's Jacobi polynomials and Laguerre polynomials. These are the three polynomials appear. So we'll discuss that.